Hello and welcome to Joey's AP Precalculus series, lesson 2.1. The title for lesson 2.1 is Rates of Change. We kind of talked upon rate of change in lesson 1.1, but actually what we are going to learn in this lesson is more like average rate of change. Build upon what we learned last lesson, we're going to be more specific on how we're approaching this, okay? So we have two lesson objectives provided by College Board directly. Lesson objective 1, compare the rates of change at 2 points using average rate of change near the points. Number 2, describe how two quantities vary together at different points and over different intervals of a function. Okay, so let's look at our first lesson objective. We're going to learn what an average rate of change is. Please fill in the blanks as I tell you guys, okay? First, let's look at the dictionary definition. The average rate of change was quite obvious, right? Between any 2 points on the graph of f is the slope of the line through those points. So average rate of change is basically the slope between points. That's all you gotta know, okay? So it's basically the slope of the line that passes 2 points, okay? That's average rate of change. Great. So we're gonna learn a thing called secant line, okay? I'm gonna explain this in a moment, so let's hold on to it, okay? So we're gonna look at this graph on the right. We learned this from pre-algebra, I believe, but we're gonna introduce to a concept called secant line. And this is really important because the same thing appears in AP calculus. Okay. So before, you were only able to find the rate of change of linear functions, right? Because the rate of change of linear function is constant. So for instance, you have the linear function here, right? The rate of change at this point, at this point, at this point, they are all the same. Why? Because the rate of change is basically change over y, change in y over change in x, right? For linear functions, the change in both x and y are constant. That's why the rate of change does not differ. However, if you take a look at this nonlinear graph, the rate of change differs. For instance, the rate of change here and the rate of change here is different, right? How can you know that? When we were like finding the rate of change of linear functions, we just took any 2 points and we just subtracted the y values over subtraction of x values, right? Let's do something similar here. We're gonna find the rate of change at a single point here and at here, okay? Based on what we learned, we're gonna state some 2 points close to each other here and another 2 points close to each other here, okay? Got it? Let's say like this is 1, 2, 3, 4, 5, 6, 7. And then let's say this is 1, 2, 3, 4, 5, 6, 7, 8. Okay. First point looks to be around 2.5, comma 7.5. The second point seems to be around, wait, it's not 2.5, sorry, it's more like 2.2, I think. The second point would be closer to 2.8, I believe. I'm not being accurate, by the way. And then the point would be like 7, right? So the rate of change here is change in y over change in x. So it would be 7.5 subtracted by 7 over 2.2 subtracted by 2.8, right? So this is 0.5 over minus 0.6. Okay? If you put that on a calculator real quick, I'm just doing this so that you can understand the concept of this, right? It's negative 0.8333, like ongoing, okay? Let me put all these kind of like aside now at the moment, like up here. Let's the same thing here. The first point seems to be around 5.2 comma 2.8. Second point seems to be somewhere 5.7 comma 2. Perfect. We're going to do change in y over change in x. Same thing. It would be 2.8 subtracted by 2 over 5.2 subtracted by 5.7. If you do that, it's going to be 0.8 over 0.5. So if you put that on a calculator, it will be negative 1.6. Oh, here it was, the rate of change was 0.833. But here, the rate of change is negative 1.6, right? So unlike linear functions where the rate of change is same over an entire region, for nonlinear functions like this, the rate of change is different for every region. Like this region, like this point around this point, can have a rate of change of negative 0.833. The rate of change over here, on the other hand, can be negative 1.6. Okay? Do you understand? So unlike linear functions, we're going to use something called secant line to kind of estimate the rate of change over a region or over a certain point. Okay? If you move on to AP Calculus, we're going to learn something called differentiation. And through this, you'll be able to find the accurate rate of change or the instantaneous rate of change at a single point. But because we're not calculus students, we're going to use something called a secant line to estimate a rate of change of a certain region or a certain point, okay? So that's where we're going to learn something called the secant line, okay? I'll tell you what a secant line is now. Okay, so I hope you understand all the concepts that I had with rate of change now. Sorry for the long explanation. Secant line, what is that? Okay, so if you want to find a rate of change of, I would say, like this point and this point, what you are doing is you're gonna draw a secant line. What I mean by secant line is a linear line that passes to these 2 points. Something like this blue graph or the blue line that I draw will be the secant line that passes these 2 points. Okay? And then if you just simply find the slope of that linear function, we know how to find a slope of a linear function, right? That's easy. Then you can estimate or find the average rate of change of these 2 points, right? Got it? So in this example, they want to find the average rate of change of this point and this point. How can we do that? We're going to take 2 points here, and then we're just going to draw a linear line. And if you find the slope of that linear line, then you're finding the average rate of change of this region. Understand? So for instance, if you want to find the rate of change of these 2 points, you're going to draw a linear line like this, or the secant line like this. And then by finding the slope of that secant line, you are finding the average rate of change of these 2 points. Hope you understand. So slope, the variable for slope is m, right? So when we are denoting the slope of secant line, we're going to use m secant or m sec. Okay? So basically, the average rate of change on the interval x1 to x2 can be denoted as m secant equals f of x2 minus f of x1 over x2 minus x1. This can be also written as this. Sorry. The location of x1 and x2 does not matter as long as they're consistent from the denominator side and the numerator side. So we basically learned that the average rate of change of a function over an interval of the function's domain is the constant rate of change that yields the same change in the output values as the function yielded on that interval of a function's domain, okay? So basically we have learned how to find the secant line and how to find like the rate of change over certain regions, right? Yeah. So it's basically change in y over change in x. We're keeping that constant, but we're building upon the constant of the secant line. Okay. Let's solve some sample examples. Find the average rate of change of f of x on the interval -3 to -1. So they're giving the interval, right? So we can just use this formula. M secant equals f of x2 minus f of x1 over x2 minus x1. x2 is -1. x1 is -3. It's given here, right? What is f of x2? We can find that by plugging in -1 to x in the original function. If we do so, it would be -2 times -1 to the power of 2 plus 4 times -1 plus 6, which would be -2, -4 plus 6, 0. Same thing for f of -1, -2, -3 to the power of 2 plus 4 times -3 plus 6. This would be -18, -12 plus 6, which would be -24. Okay, I'm gonna rewrite this here, and I'll erase my messy calculations. Great. So we're just gonna plug into the function to the equation that we have, right? So it would be 0 minus -24 minus 1 minus -3, 24 over 2, which is 12. So the average rate of change of this region can be understood to be what? 12. Okay. Hope you understand what I'm doing right now and kind of understand how the concept works here. Basically, what I did is from this function, I drew a secant line that passes these 2 points and found the average rate of change of that linear function. Okay, great. Let's do the same thing here. I told you msec is equal to f of x2 minus f of x1 over f x2 minus x1. x2 is 5, x1 is 2. F of x2 can be found by doing this, and then same thing for this. So this plug in -24, -6, 5 minus 2, -30 over 3, -10. So the rate of change for this function in this interval would be -10. Let's sign some more advanced word problems here. The formula for the distance traveled by falling objects on the moon is d of t equals 2.7 t squared, where d of t is the distance in feet and t is the time in seconds. Find and interpret the average speed of the object for the time interval 1 to 2 seconds. I told you this thing, right? Same thing applies here. Instead, it's a real world problem now, right? x1 is 1. x2 is 2 because they give you the time interval, right? F of x1 can be found by plugging in 1 for t, which is 2.7. Same thing can be found for f of x2 by plugging in t for 2. So it'd be 2.7 times 4. If you calculate that, it would be 10.8. Let's plug into this function again. 10.8 minus 2.7, 2 minus 1. It would be 8.1 over 1. So the right answer would be 8.1, right? But this tells you to find and interpret the average speed, right? The unit for speed is what? Distance per time. The unit for distance is feet and the unit for time is seconds. So the right answer for this question would be 8.1 feet per sec. You have to keep the units to be marked as correct. Same thing for this. We're going to do the same thing. We're going to use the same formula because we have to find the average rate of change, right? Or the average speed within this interval. So x1 is 2, x2 is 3, f of x1 is what? 2.7 times 4, and f of x2 is 2.7 times 8. Sorry, 9. If you do that, if you do the calculation on a paper, you would get 10.8 and then 24.3. If you do that, it's going to be 24.3 minus 10.8 and then 1, right? Because 3 minus 2 is 1. And then if you do that as well, you will be getting 13.5. We're going to keep the unit as well. So the answer would be 13.5 feet per seconds. Okay. Now let's move on to lesson objective 2. Lesson objective 2, what was it? We're going to now learn how two quantities vary together at different points over different intervals of a function. So we're going to learn increasing, decreasing, and constant functions, okay? Fill in the blanks as well, please. First definition, a function f is increasing on an interval I if and only if for any 2 points in I, a positive change in x, and a positive change in f of x. Okay, what this is saying is it is increasing if change in x is positive and if change in y or change in f of x is positive. So let's say there's change in y and change in x, right? If both are positive and positive, if both quantities, the independent variable and the dependent variable, if both are positive at this region or at this interval, then the function is increasing. For instance, if you take a look at these 2 points, let's say this is 1 and this is 2, and let's say this is 1 and this is 2, okay? And this is 1, comma 1, this is 2, comma 2, right? What is change in y? Change in y is 2 minus 1. It is positive. What is change in x? 2 minus 1. Also positive, right? Because it's positive over positive, this is called an increasing function because it's increasing in this interval, okay? Another way of thinking is if f of 2, which is the second point, is greater than f of x1, when x2 is greater than x1, then it's increasing, okay? But just think that if change in y over change in x is plus over plus, then it's increasing. What's the opposite now? We're going to find when it's decreasing. Definition: if the function f is decreasing on an interval I, if and only if any 2 points in I, a positive change in x results in a negative change in y. So you know there's change in y over change in x, right? Now, if change in f of x is negative, and if change in x is positive, this constitutes for decreasing function. I'll prove you why. let's say that it's the same 1, 2. So this is 1, 2. This is 2, 1, right? What is change in y? It's 1 minus 2. What is change in x? 2 minus 1. It's going to be negative and positive. Oh, change in y is negative, change in x is positive. So it's decreasing. Another way of thinking it is if the y value for x1 is greater than the y value of x2, when x1 is smaller than x2, then it's decreasing. But really just think like this, okay? Last thing is constant. When is it constant? If a positive change in x results in a zero change in y. What I'm saying with this is if change in y over change in x is something like zero change over positive, then it's constant. Also prove you why. Let's say that this is 1, this is 2, and let's say this is 1, right? That's 1, 1, and then 2, 1, right? What is change in y? 1 minus 1, 0. What is change in x? 2 minus 1, 1, positive, right? So it's 0 over positive. In that scenario, we call that it's a constant function. Hope you understand this. Let's solve some example problems. How many do we have? 2 more left. Great. Use the function of the function f of x. Estimate intervals to the nearest 0.5 unit on which the function is increasing, decreasing, or constant. Support the answer numerically. When you're asked to support the answer numerically, you have to make a table, right? Yes, we have to. We're almost done. Okay, now let's look at the graph first. I told you that it is decreasing when what? The rate of change of y and the rate of change in x. In this scenario, if change in y is negative and change in x is positive, then we call this decreasing. When change in y and change in x are both positive, we call this increasing. When change in y over change in x is 0 over positive, we call this constant. Keep in mind of this as we are solving the problems, okay? Okay. So if you just take a look at the graph, and then let's just take a look. With common sense, you can know that if you just have these 2 points, and if you were to find the rate of change, because the second point is small, and because the first point is positive, right? And then because it's f of x2 minus f of x1 for the change in y, if it's negative minus positive, it's negative, right? So it dissatisfies, and then for the x values, this is a negative value, and this is a negative value that's close to 0. Let's say it's 0. If it's 0 minus negative, because negative, negative, it's positive, right? So this is also fulfilled. So we can say that this point, this region, that thing I colored in black, is decreasing. Let's the same thing for here. I'm gonna have these 2 points. Let's say that this point is like 3, 4, not accurate. Say this is like 0, -4. Change in y, 4 minus 4. Change in x, 3 minus 0. Both positive over positive. So this part, the red part, is increasing. So basically, we already know the answer. If you were to write the answer, we can say increasing part is from negative infinity to 0. We can say decreasing is 0 till positive infinity. You should always use round brackets because at x equals 0, it's neither increasing nor decreasing. neither increasing nor decreasing. It's more like constant, okay? Great. Now we have to support the answers numerically. All you got to do is just draw a table. I'll do it here by looking at the graph. Okay. Okay, if you take a look at this, you can note that till 0, it's decreasing, right? And then from 0, it's increasing. So our answer is supported by numerical evidence. Let's do the same thing for this. Okay, by just looking at this, we can know that this region is what? Decreasing. We can know that this region as well is decreasing. We can know that this blue part is increasing. If you're curious why, try to do the rate of change thing as I did for the previous question. Let's support our answers numerically by drawing a table. Okay. Of course, I'm not doing this in my head. I'm I'm looking at the answer sheet, by the way. Okay. Okay, so if you take a look at this looks like 0.05, negative 0.05. This looks like positive 0.05. Okay. So till negative 0.05, you can see that it's decreasing, right? And then from negative 0.05 to positive 0.05, we can see it's increasing, right? And then from positive 0.5, it's again decreasing, right? So you can see this kind of pattern here. And we can write the answer as decreasing, negative infinity to negative 0.5, or positive 0.5 till positive infinity, and it's increasing from the region of negative 0.5 till positive 0.5. Make sure to never use a square bracket because you are never including these points because they're neither decreasing nor increasing. Hope you now understand and perfectly apply the concept of rate of change in all the questions you do. If you have any questions, just feel free to email me. And thank you for listening to my lecture.